Yeah. So hi all. I'm Meri Teeriaho, and I'm alumni of the AstroCamp. I was a camper in 2020, and today I'm going to talk about the local group and how to estimate its mass by using a machine learning. So this presentation is based on a paper that we published last year, and also it's based on my bachelor thesis that I did last year. So first, some things about me. So I'm theoretical physics student at University of Helsinki in Finland, and I'm now starting my third year as a bachelor student. So last year, I was a research assistant at University of Helsinki, and I was able to write a paper with Dr. Til Savola and Professor Peter Johansson. And the title is The Local Group's Mass, probably no more than the sum of its parts. And in that paper, we went through some ways to calculate the local group's mass, and my contribution was to do the estimation using a machine learning. And I also wrote my bachelor thesis about that. And there is a picture of me. I'm using a traditional Finnish graduation cap that you will get when you graduate from high school. And after that, you can use it at university events. And in this presentation, I will talk about the local group in brief, and then I will talk about UTSU cosmological simulation because we gathered our data from that simulation. Then I will talk about machine learning and how we use that in our research. And then I will present the results of the mass of the local group. And there is a picture of Andromeda and Milky Way colliding. So the local group is a galaxy group that has 50 members, and most of them are dwarf galaxies, but the biggest galaxies in that group are Milky Way and Andromeda. And they are colliding in 5 billion years. And in this picture, I'm sorry, it may be small, but you can see in the center the Milky Way and then the Andromeda hovering over it, and also some dwarf galaxies that are around those bigger galaxies. So then some things about dark matter halos. So you probably know that 84% of the matter in the universe is made of dark matter. And after Big Bang, when the dark matter was created, it started to form dark matter halos by gravitation. So dark matter halos are areas that has a lot of dark matter. And the baryonic matter, so the kind of a normal matter, followed that dark matter to those halos and started to form stars and galaxies there. And because of that, most of the mass of galaxies are from their dark matter halos. And that is also the case for Milky Way and Andromeda. And here is one drawing of galaxy, and you can see that the dark matter is kind of around the whole galaxy, and it takes a big part of the galaxy. So how can one examine the mass of the local group? So first of all, the mass of the local group is really important value in cosmology and astronomy. If we know the mass of our own galaxy group, we can learn more about other galaxy groups, and we can also examine is the local group mass congruent with the lambda CDM model. And usually we approximate the mass of the local group to be just the mass of the Milky Way and Andromeda. And sometimes we just consider the masses of the galaxy's dark matter halos. So we don't look at the baryonic matter, the normal matter. And one common way is to examine the kinematics between the galaxies. So the kinematics are related to the mass of those galaxies or to galaxies, but we can't directly measure the mass, of course, but we can measure the kinematics or make some observations of those. And when I say kinematics, I mean the tangential velocity of the galaxies, the radial velocity between the galaxies, and also the distance between galaxies. One really popular method is timing argument method. So one popular method to examine the local group mass. And this was created by Kahn and Voltier, 1959. And it uses two equations, Kepler's third law and specific orbital energy. And you can see that they are using the same kinematics. So here is the distance, the d, and then the relative velocity between Milky Way and Andromeda. And if you calculate the mu out of the equation, this part, you will get the value for the local group mass. So in this case, the Milky Way mass plus the Andromeda mass. And you can see that they are not using the tangential velocity, but this was added later. I don't now remember who did that, but yeah, it was added later. And Kahn and Voltier got the minimum value for the local group mass, which is 1.8 times 10 to 12 solar masses. So then more about our method. I will first talk about UTSU simulation because we gathered our data from it. So here is a picture of UTSU simulation, which is a kind of a simulation of universe. It's a dark matter cosmological simulation, and it has 2.1 trillion particles, and the width is 9 billion light years. And it uses Planck cosmology, so cosmological values from Planck mission. And you can see that it's really precise. So you see, first of all, the kind of foam-like structure of universe. But if you zoom in, you will start to see those dark matter halos, so those light points that could be, for example, galaxies. But we won't use the whole data. We just want to find some local group candidates from the UTSU simulation. So we search for dark matter halo pairs that would represent Milky Way and Andromeda, and in this way, the whole local group. And those pairs should have suitable masses, distance, and radial and tangential velocity. So we will use some limits for the masses and distance, because we know that the Milky Way Andromeda they can't have some masses that are really high or some distances that are really, really large. So we are limiting the data and then choosing some pairs that are useful for us. And we got over 1 million pairs. In this figure, you will see all the pairs. And if you zoom in, you will start to really see those pairs. I'm not sure if you are really able to see them, but here, for example, we have red and blue dots together. So these are the pairs. So the blue dot could be, for example, be Andromeda, and red point, the Milky Way. So now when we have the data, we can start to look at the machine learning part. So we used supervised machine learning. And first, when you're using supervised machine learning, first the algorithm learns the connections between input variables and the target variable from a given data set where both are known. So in our case, the input variables are the kinematics, and the target variable is the local group mass. So the mass of the Milky Way plus the mass of the Andromeda. And then the algorithm generates a model based on its learning. So now when we put the input variables in the model, it will predict a target value for us. So after we have trained the machine learning algorithm with the UTSU data, we can put some observations of the kinematics inside the model, and it will tell us mass that is correlated to those kinematics. And here is a picture of that. So we have two steps. So first we will train the data. Here is a little part of the UTSU data that we used. So here are the kinematics and then the total mass. So the local group mass. And from the simulation, we all, of course, know all these values because in the simulations, you can calculate the total mass. And we can put it in the black box in the algorithm. And there is a question mark because we can't really know what happens inside it. Or you can know it, but the algorithm is pretty hard to describe. So I won't tell more about it. But after that, we will have a trained model and we can put some kinematics inside it. So now we don't have the mass values. And we have two rows and we will get two mass values for each row. We can also test the model before we really use it to produce results. We can separate the data to training and testing data. So this upper part is for training data, and the data in this red box is the testing data. So first it learns the connections from this training data, and then we will put these kinematics from the testing data inside to the model, and then it will produce some prediction mass values. And we can check that are there correlated with these kind of a real mass values from the simulation. So if the model is really good, it will produce exactly these mass values, but that is, of course, isn't the case usually, but something close. So we can see that how good the model is. And here is a figure of the algorithm that we used. We used gradient boosting regressor 3 algorithm. And if the algorithm is perfect, it should follow this black line. So the predicted mass is always same as the real mass from the test data. But our algorithm isn't a perfect. You can see that it has correlation. So here are the points, all the prediction points, and then the line that is fitted to those points. And the slope is 0.476. So yes, those points have correlation, but it's not a perfect. And the color represents the point density. Yeah, so now we know that the model is working. It's not perfect, but it has some correlation. So it predicted mass values that are close to the real mass values. So now we can really start to produce the results. So first we will choose some observations, and we used observations from Van der Moor et al. Papers, and they got their observations from Gaia satellite data. And here are the values for the kinematics that they got. So here's the radial velocity, distance, and tangential velocity. And because we have a mean and standard deviation for each value, we can make normal distribution for every kinematic value. And then we can choose 10,000 random points from each distribution. So we would have 10,000 points for radial velocity, distance, and tangential velocity. And then we can put that data into the trained machine learning algorithm, and we will get 10,000 mass values corresponding to the 10,000 rows of the kinematic data. And this is called Monte Carlo method because we are like randomly using points from the normal distributions. Then we can plot all the mass values that we got, so the 10,000 lower group mass values. And then we can get the median out of the histogram and also the minus sigma and plus sigma values. And here is the result. So we got that the mass of the local group is 2.3 times 10 to 12 solar masses. And there are also the errors. And then some other results for the local group mass. So I used the gradient boosting regressor 3 algorithm in my bachelor thesis. And this is the result from the previous slide. Actually, this is not a correct value because I have a 1 unit mistake. So I just use this value to show you how the algorithm works. But actually in our paper, we use a Gaussian progress regression algorithm. And from that algorithm, we got this value, so 3.2 times 10 to 12 solar masses. And it's higher than the gradient boosted regressor 3 result. And then some other results. So the timing argument method usually produces slightly, or not slightly, just higher results. And then there is also one result from other paper that use machine learning. And you can see that that value is closer to our value. So then some conclusions. Using simulation data and machine learning is a new numerical way to examine the mass of the local group. So this, you can use this method. This is really new way because we are really using simulations and machine learning that are really new things, and you need to have powerful computers to produce the simulation and also run the machine learning. The chosen machine learning algorithm, the gradient boosted regressor 3, it produces a good model, but the result of the local group mass was smaller than the other results, even though it was accurate. But now we know that it's from the unit mistake, so we shouldn't look at that value. But the Gaussian progress result was higher and closer to the other results, and it is also relatively accurate. And here are the links to the pictures that I used. And thank you that you listened. If you have any questions, I think you are free to ask now or soon.